Alright, for this second and last part of Stokes' theorem, we are going to evaluate, or rather, evaluate a line integral. But in this case, what we're going to do is verify Stokes' theorem to obtain the circulation over the hemisphere x squared plus y squared plus z squared equals to 4 for z greater than or equal to 0. Okay, number one, what does that mean? Is that the upper hemisphere or the lower hemisphere? Upper, right? Because it's z is positive, and c is the trace of s in the xy plane. How do we get the trace in the xy trace? Remember traces? Set c equals to 0, right? So, okay, z equals to 0. C is the trace. So z equals to 0, so that is x squared plus y squared plus z squared equals to 0, equals to 4. So x squared plus y squared plus 0 squared equals to 4, which means x squared plus y squared equals to 4. So in this case, well, the trace for sure is on the surface, right? Yes. Well, of course, the driving force, the force field is z minus y, x, negative x. So here in this case, verify means to do both sides of the equation in Stokes' theorem. So we have to solve the same problem twice, by the way. Hold on, what does that mean? What equation? Well, this is the equation here because this definition right here is an equation. There's two sides. So that means number one, we have to get the circulation the old-fashioned way by parameterizing the trajectory, which is pretty easy. It's a circle, come on. And number two, using Stokes' theorem, which is our new way to calculate the circulation. Well, okay, let's do both. Let's do this. Number one, let's go back to the exercise, and number one, let's plot the trajectory right here, which in this case it's that's a circle, right? That's a circle of radius. What was that again? Radius 2, right? So, and again, the implications of the line integral and the implications in this case of our the implications of our surface is that of the orientation that is going to go counterclockwise, right? Okay, so let's forget about Stokes' theorem. Let's go back to basically type 2 line integrals where we have our driving force in this case and trajectory to go along with. Okay, so what is that? How are we going to parameterize this? Okay, how do we parameterize a circle? R of t. Okay. So what are the parametric equations of the circle of radius 2?
2 cosine t, 2 sine t.
2 cosine t. 2 cosine t. 2 sine t. But hold on. Because we have a force field in space, what would be the z component of this circle? 0, right? And 0. Okay, I believe this was the same. Wait, was it a sphere of radius 3 I did? Oh yes, it was a sphere of radius 3. So it's a circle of radius 3, right? Oh, it was a radius 2. Never mind. Oh, hold on. Yeah, it was radius. Oh no, yes, it was radius 3. Radius 3. So, okay. So let's put a 0 there. What else do we need? Oh, we need the dr, right? The differential dr for a type 2 line integral. So that is negative 2 sine t, 2 cosine t, 0 dt. Okay? So let's evaluate the line integral. So that is the integral along the closed circuit here, the closed curve C of f dotted with dr that equals, what's that? The integral along C of the force field z minus y comma x comma negative x. Okay, and that dotted with our dr, which is what we just got in the previous part, that is negative 2 sine t comma 2 cosine t 0 dt. Alright? Oh, hold on. Before doing this dot product, should we? Okay, yes. Again, let me do some highlightings here. So let me highlight the x component. Let me highlight the y component. Let me highlight the z component. Well, so the z component, that's where we're going to replace with the force field, where it corresponds for the variable z. And then y, it's going to be the one in green, and x, it's going to be with red, purple, or pink rather. Right? Because we want an integral with respect to t, and what do we have? X's, y's, and z's, so we need to write those in terms of t's. Okay? So let's go about it. We will put the limits in a second, which I think they're pretty obvious, alright? Okay. So this will be the integral along the closed curve C, okay, of z, which is 0 minus y 2 times sine t, comma x, which is 2 cosine t, comma negative x. Careful, that's negative 2 cosine t. And dot it with the dr differential we got from before, that is negative 2 sine t 2 cosine t 0 dt. Okay, let's evaluate this dot product before we can integrate this, before we can put the limit to the integral. Okay, so this is component wise, this green with this green, this purple with this purple, it's kind of blue, gray-ish, and this sort of purple with purple. All right, component wise. All right, so that's the integral along the closed curve C. The dot product yields a scalar, no longer a vector. So negative 2 sine t times negative 2 sine t, isn't that positive 4 sine squared t, plus 2 cosine times itself, that's 4 cosine squared, and negative 2 cosine t times 0, that's just 0, close parentheses, dt. And well, what do you say? That's the integral along the curve, the closed curve, that's 4 sine squared plus cosine squared dt. And you know this identity equals to 1, right? So that'll be then that equals to 1, and that's simply going to be 4 times the integral of dt, but I'm going to put the limits from 0 to pi. Alright? Because in this case, yes, we need to be careful here, because even though they're telling us it's the upper hemisphere, the solid part, they're not telling us anything about first octant or the like. So upper hemisphere involves the entire hemisphere, which involves the entire trace in this case, which is that circular trajectory. That's why the limits are going to be 0 to 2 pi. Alright? So, I mean, evaluate 4 times t from 0 to 2 pi. Okay, that is 4 times 2 pi minus 0. So, this will be equal to 8 pi. Final answer. Okay, so that is the result using what? Using the line integral, which not bad, right? It's pretty easy to solve. Okay, part B. Let's go to the next page, and we will do the same problem again, but this time using the Stokes' theorem and verify that the result is the same. Okay? All right, let's take a deep breath because this one is gonna take a good minute to go. So I know this is weird because the pattern is that we are learning a new tool supposedly to solve a problem that might have been longer to solve using the line integral parameterization. So either the Green's theorem, the Stokes' theorem, the divergence theorem is supposed to, in a way, to kick in and solve the problem easy for us. Well, that's not always the case. When this part for this particular situation, it's not going to be the case. But still, we have to verify. Plus, it's good practice for our integration techniques. All right, number one. Let's recall what our driving force is. That is big F. That is the z minus y, x, negative x. Okay? Well, in this case, for Stokes' theorem, we need to work with the surface. And the surface is given in the form of the equation of a sphere given by x squared plus y squared plus z squared equals to 4. Okay, so let's solve for the variable z because for the surface we need a function of x and y as independent variables where z will be the dependent variable. Okay, so z squared equals to 4 minus x squared minus y squared, and z equals to the square root of 4 minus x squared minus y squared. And again, you might argue, why didn't I put the plus minus? Because the problem is telling us the equation of the surface, the sphere, and it's also giving us an additional condition. Z is greater than or equal to 0. So given that condition, z greater than or equal to 0 in the previous page, right here, with this, there's no place for the negative radical in a similar situation as another problem we did before. All right? So we're good right here. We need to find the partial derivatives. Okay, number one, let me rewrite the function. That's z equals to 4 minus x squared minus y squared to the 1/2. And let's find the partial derivatives. That is z with respect x equals, so that's a 1/2 times 4 minus x squared minus y squared to the negative 1/2 times the derivative of the inside with respect x, that is negative 2x. Alright, so what's that? Simplify to get, well, I think we did something like this before, right? That's a negative, and I think it was the same surface. Anyway, I think there was a 16 instead of a 4. I don't know. But the derivatives were computed the same way. And likewise for z with respect y. For z with respect y, what's that? Same. Just replace the x with a y. Negative y over the square root of 4 minus x squared minus y squared. Okay, let's see. Oh, what else do we need for Stokes' theorem besides the partial derivatives? What else? The curl of the vector field. Okay, so the curl of f, that'll be, again, we write the formula first, p with respect y minus n with respect z I minus p with respect x minus m with respect z in the direction of j. So that's the rotation about the y-axis plus the rotation about the z-axis, which is n with respect x plus, what was that? Oh, no, not plus. It's minus m with respect y. Okay. Let's find the partial derivatives. Oh, what's P, what's M, what's N? Well, label your vector field. So this is our M, this is our N, and this is our P. Alright, careful with all these minuses and pluses that we're going to work with. Okay, P with respect Y. Well, there's no Y's there, so that'll be 0 minus N with respect to Z. Oh, there's also no Z's at all there, so also 0. I minus P with respect X. Oh, that's a negative 1. M minus M with respect Z. Oh, that's just 1. J plus N with respect X. That's another 1. Minus M with respect Y. Oh, careful here. Minus negative 1. K. Okay, so 0 minus 0. Isn't that 0? Okay, so let's go and change this to component form. Now, careful. Let's spam this. Let's spam this first. The inside of the parentheses, that's a negative 1 minus 1, which is negative 2. Times the negative outside, isn't that positive 2? Okay, and lastly, oh, careful with these minuses right here. Minus becomes a plus 1 equals to 2. Okay, we have everything we need. Yes, we do. We have everything we need to set up the integral for Stokes' theorem to verify Stokes' theorem. All right? Okay. So we're going to evaluate the line integral. Well, not the line integral way we already did. F dotted with dr. That equals instead the double integral over the region R of the curl of F dotted with negative Z with respect X comma negative Z with respect Y comma 1 dA. No more ds because this negative Z with respect X, negative with respect Y is times dA is the result of changing that what was that? That surface area element. We already did that in the previous couple sections, okay? Alright, so we have everything we need. Let's substitute and we will iterate later. For now, let's write the double integral over the region R. And let's write the curl vector, that is 0, 2, 2. Okay? I'm not going to have enough space. Maybe not. Okay, let me make it smaller, move it. And that dotted with, okay, careful, because you see how these partial derivatives, again, they're negative, and the vector in the integrand is negative. Those two negatives, all four negatives, get canceled out and become positive. So that is x over the square root of 4 minus x squared minus y squared, comma, y over the square root of 4 minus x squared minus y squared, comma, 1 dA. Alright? Okay, the next is a huge dot product. Well, at least the first one, 0 times x. Well, let me color code just so we can see the different components. So 0 times this madness here, and then what else? 2 times all this other madness there, and lastly 2 times 1. Okay, so multiplying the green one 0 times whatever, it's just a 0. Okay, so that's the double integral over the region R of 0. 2 times this quantity is plus 2 times the quantity 4 minus x squared minus y squared, plus 2 times 1, which is 2. And again, this is a scalar. This is no longer a vector. The result between performing the dot product between two vectors is a scalar, not a vector. That's the cross product, all right? Okay. 2y. Oh yeah, 2y right here, right? 2y. Thank you. Very important. Okay. Let me just simplify this, okay? That'll be, let me just get rid of this, clean up the 0. So 2y over the square root of 4 minus x squared minus y squared plus 2 dA. Alright, let's have a look at this integral right here. Okay, any ideas how to evaluate this integral? I mean, how do we iterate dA? dy dx, dx dy? Polar form. Okay, why polar form?
Because you get an R on the bottom.
So that's one of the reasons. Number 2, the most important one, that's because we're integrating over a circular trajectory, right? So polar will come in handy here. All right, so number 1, this guy right here will become negative r. Well, let me write it down. Negative x squared plus y squared, which is negative r squared, which is simply negative r squared. And what about y? Isn't that r sine theta? Right? R sine theta. Okay. So, all right. So that means, okay. So that means we are going to set up the following integral. That's the double integral of 2r sine theta over the square root of 4 minus r squared plus 2. And in this case, change dA with r dr d theta. And the limits, okay, what are the limits for the radius 0 to 3, right? And the limits from 0 to 2 pi, right? Looks like a very harmful integral. I mean, because how many integrals like this we have evaluated before? Too many of this already, right? There's a little catch to this because I solved this problem a few times. And when I want to go this order, the order dr d theta, it becomes a mess. And there's a point where I just go in circles and I'm not able to solve the problem. It gets crazy actually. Actually, let's see. So what was the issue here? Okay, yes. Yes, radius 2. Yeah. Anyway, you're right. Thank you. So, let me keep simplifying this integral a little bit further. 0 to 2 pi, 0 to 2. Oh, you will see it better actually. You will see the issue a lot better. Okay. So that'll be 2r squared sine. So I'm distributing the r, right? Over the square root of 4 minus r squared plus 2r dr d theta. Okay, look at that problem. Okay, let's say you want to go the dr direction. Okay, what do you think about the dr direction? What would be your strategy to go about dr? I mean, integrating with respect r. U sub? No? Do we have a case for a U sub? What is this? What is that integral a case for? Trig sub? Do you want to do a trig sub? No? I mean, it's fun, but I mean, at this one time we want to be efficient, right? Even though you already equipped with all these tools, but I mean, one of the best tools you want to use is efficiency. Okay, now think about integrating instead with respect theta first and then with respect r. What is the integral of cosine? Sine. Okay. I mean, what's the integral of sine? Oh, reverse. Oh, okay. Sine is, well, not cosine, right? So it's negative cosine. So negative cosine of upper limit. What's cosine of 2 pi? 1 minus cosine of 0. Same. Do you see how that integral is going to get zeroed out? Killing the 2r squared over the radical, and that's how you're going to bypass the trigonometric substitution. That's how you're going to kill that huge factor. So reverse the order of integration, and in this case we can simply use Fubini's theorem. Remember that theorem? Because we're integrating over a rectangle. Yes, I know, a circular rectangle or polar rectangle, but I mean by rectangle we mean when the limits of integration are just numbers, are just constants. Do you see variables in the limits? Which is awesome, right? That means we can simply reverse the order. All right. So that is the integral from 0 to 2 and from 0 to 2 pi, the same integrand, that is 2r squared sine theta over the square root of 4 minus r squared plus 2r d theta dr. All right? D theta dr. This is the first time we ever reverse the order of integration for a polar integral, right? Well, that's because it's going to be helpful here, all right? Yes. Okay, so the integral, okay, 2r squared over the square root of 4 minus r squared is just going to be a constant, right? With respect theta. That is the integral from 0 to 2 of sine, that'll be number 1. Negative 2r squared cosine theta over square root of 4 minus r squared plus 2r theta evaluated between 0 and 2 pi. And again, these limits of integration are only for the variable theta. I mean, I don't think at this point in time I have to do this highlight. You guys know how this works, but just in case, there's a lot going on here. Don't forget the dr, not the theta. Dr. Upper limit minus lower limit. Okay. So that'll be the integral from 0 to 2 of negative 2r squared over the square root of 4 minus r squared times, okay, what's that? Cosine of 2 pi minus cosine of 0. Come on, they're the same value, right? And then plus 2r times 2 pi minus 0 also. Okay? Dr. And just look at this beauty. Alright? 0. 0. No more trig substitution. I mean, if you want to try the other way, again, story mode versus hero mode, you want to go hero mode, go for it for the sake of practice at home, right? Okay, so that is the integral from 0 to 2 of 2r times 2 pi. Well, that's actually 4 pi r dr. Take out the 4r, the 4 pi, 0 to 2 r dr. That equals 4 pi r squared over 2 from 0 to 2. That reduces to 2 pi times 2 squared minus 0 squared. 2 pi times 4 minus 0. Isn't that the same result as that we obtained by evaluating the line integral, type 2 line integral, parameterizing the circle? But again, I mean, I know Stokes' theorem is or this vector calculus theorems are supposed to help us simplify the work by a lot, but in this case, I mean, yeah, yes, sort of, right? All right. Well, I mean, that's thanks to the reversing the order of the integration. Otherwise, it would have been